Okay, I think we'll go ahead and get started. Thank you all so much for being here tonight. We really love doing these nights and interacting with you all and hearing your questions. So I appreciate you making the trek and dealing with the registration system. I know that that is not the easiest, and thank you so much. We have a great set of talks and some questions for you all tonight. I'm very excited to see the talk myself. My name is Amanda. I'll be your MC for the night. You get most of the emails from me, so I'm sorry for the spam. I hope they are helpful. Please feel free to give feedback at any time. All right. So we'll start with some trivia. These are questions you might not have any idea about. And sometimes those are the funnest things because you have to think more about them than if you just know a fact off the top of your head. Then we'll go through some announcements about events that are coming up for the summer. We'll hear our talk from our fabulous speaker, Jing Yao. Then we'll do Q&A, so any questions you have from her. We'll do a raffle, and unfortunately, there's no observing tonight. We as astronomers at Columbia have really bad luck, apparently. We have not been great at picking nights that are going to be clear, but we are going to have some more opportunities this summer to observe, so hopefully they will work out. Okay, so we'll start with trivia. How this is going to go, I'm going to do the same procedure I do with my students in my class. So I'll show a question. It will be multiple choice. I'll give you all some time to think about it. You're welcome to whisper with people around you. And then I'll have you vote. So it's A, B, C, D. So you'll show me 1 for A, 2 for B, 3 for C, 4 for D, just so I can see what folks are thinking. And then we'll go through the answer. So our first question, I want to make sure I don't accidentally skip ahead. Okay. About how many stars do we think there are in the Milky Way, our home galaxy? 1 million, 100 million, 1 billion, or 100 billion? So take some time to think about it. Consult folks around you if you want. And when you're ready, let me see what you think. Okay. We've got a lot of 4s. I see some 3s and 2s as well. And our answer is 100 billion. So that's a lot. We use billion all the time. I'm very dramatic. I say it's a billion degrees out or I have a billion emails to go through. So I lose track of how big a billion actually is. But a billion is incredibly large. That's more than we can count in our lifetimes. If you do the math, that would be more years just trying to count to 1 billion, let alone 100 billion. We can't see our own Milky Way galaxy because we're in it. That's like if I asked you all to take a picture of the building, you'd have to go outside, cross the street, take a picture. We don't have time to do that. So we have to make do with some observations that are around us to get this estimate. Question 2, a similar question. How many galaxies do we think are in the observable universe? So you just did stars in a galaxy. Now let's think about galaxies in a universe. People seem less confident about this one. There were some really fast answers before. All right, this time I really see all of the choices being represented. I think that's very fun. And our answer here is 1 trillion. So about 10 times the number of stars. I was already impressed by the number 100 billion. Now we've got 10 times that. And again, this is an estimation. I tell my students that astronomers, we're not exact at all. 3 million, 5 million, that's the exact same thing to me. So of course, we don't know exactly how many galaxies there are in our universe. We do our very best to estimate, and then we shrug our shoulders as astronomers and we're at peace with how rough the estimate is. All right, question number 3. Which is a real kind of galaxy? Astronomers love naming things. They are notoriously bad at naming things. Only one of these is a real kind of galaxy. Okay. And our answer is a starburst galaxy. So this is a real kind of galaxy. Our own galaxy is named the Milky Way, but that's not a specific kind of galaxy. Starburst galaxies are galaxies that are forming or making new stars rapidly. And you'll hear a lot about galaxies forming stars from Jing Yao in a couple of moments. Okay, question number 4. The Milky Way and its sister galaxy, Andromeda, are going to collide in billions of years, so don't let this keep you up at night. How fast will they be going before the collision? We've got quite the range of speeds here. And these are all in miles per hour, which is a unit astronomers don't use, so I had to look up the conversion. Okay, let's see. With this one, I'm seeing a lot of 2s. Yeah, I would say I see mostly 2s, some 1s, some 3s. No one thinks 6 miles per hour. And you all were right. Our consensus was 600,000 miles per hour. That's really fast. No matter how fast you try to go in your car, you cannot go that fast. Our rockets aren't going that fast. It's truly the astronomical objects in our universe that are going so much faster than human scales. So this will be quite the dramatic collision and dance between these two galaxies. All right, question number 5. I tried to put these in what I thought were easier to harder. So if you're starting to feel like you need to think more, that's on purpose. All right, which part of the Milky Way forms the most new stars each year? So our galaxy has different parts: the halo, the thin disk, the thick disk, and the bulge. Which one has the most new stars forming in it? Okay, I'm seeing a variety. I think I maybe see most 3s and 4s. The answer is B, the thin disk. So as this name suggests, it's a very thin, on galaxy standards, part of our galaxy, still very large on human scales. Okay, so hopefully you learned some things from trivia and you're gonna learn so much more from Jing Yao. I'll go on to announcements. So you can join our mailing list. That's the best way to find out about events. We also have an event calendar on our website. We're going to have 2 more lectures this summer. Our very next one is going to be our first daytime one, and we'll do some solar observing. So hopefully everyone here knows you should never look at the sun with your eyeballs. You should never look at it even if you're wearing sunglasses. You definitely don't point a telescope at it, but we are going to have special equipment that lets you see the details of the surface of the sun, and we'll have a talk about the sun as well. Then August 8th, we'll have our traditional night lecture with hopefully observing. And if we do any observation events between then, we'll advertise on our mailing list. We're also partnering with the Queens and New York Public Library systems to do events aimed at children. So if you subscribe to any kind of New York or Queens Public Library listservs, they'll have advertisements about those. And then I got this morning, so fantastic timing. We're partnering with CUNY to have an event where we're going to be all together looking at the first images from a telescope called Vera Rubin. It will be the first time for us astronomers as well. This is on Monday, June 23rd from 10 a.m. to noon. It won't be in this building. As soon as this lecture is over, I'm going to send out an email with information, including a registration link. But this is going to be really cool. You'll get to talk with astronomers. And like I said, see images that for the first time, everybody else in the world is also seeing, except for the astronomers who processed them. Okay. And with that, I'm going to pass it off to Jingyao. She's a graduate student in the department. She once gave a talk in my class, so I know this is going to be a fantastic lecture. If you have any questions, we'll be taking them at the end.
And people in the back hear me okay? All right, awesome. Okay, thank you so much, Amanda, for the amazing introduction. And welcome to today's lecture where we talk about how do you starve a galaxy. Again, my name is Jingyao Zhu. I'm a PhD student in this department, and I study galaxy evolution. So this is very much of my wheelhouse. First of all, to orient ourselves a little bit, where are we in our galaxy? I hope that you didn't have too much trouble finding this building. This is the Pupin Hall in the Morningside Heights area, and we're in the city of New York. So if we keep zooming out and out, we'll eventually see we're on the planet Earth. And if you look at the faint background over there, this is a picture I took from Google Earth. And the faint background in the back, it looks whitish, milky-ish. That is indeed our Milky Way galaxy. Amanda has already showed this image, but our sun over there is really just one out of 100 billion stars in our galaxy. So this image here, you're looking at a disk face on, but in fact, this is a pretty thin structure. So if you see it in 3D, it's going to be something like this. So this is as if you're looking through this disk from an edge-on view, and our galactic disk is that central thing over there. Our sun is somewhere in there. All right, so anatomy of our galaxy. What's in our galaxy? You can probably not see this in New York City, but if you go upstate or somewhere else where it's really dark, you can see the different stars as seen from the upper panel in our galaxy. And those whitish, milkish color, and that is many stars stacked together. So they're so dense, you can't tell them apart. There are many stars showing those white lights. There are 100 billions of them in there. And the second map, which is more interesting, I don't see them with our naked eyes. This is a gas map. This is mapping the carbon monoxide. It's bad for humans, but they're in our galaxy, which is tracing the larger hydrogen gas in our galaxy. Why can we not see it? Because it doesn't emit in the visual light. It emits in radio wavelengths. And in fact, this very image was taken in the 20th century, some 30 years ago, on this very building. It is taken on the Pupin roof. There used to be this small 1.2 meter telescope over there, but I think now it's gone. It's more an educational telescope now. Okay, so the stars and gas in our galaxy actually talk to each other. They're not in isolation. In fact, they're in this active life cycle. Let's start with our own sun, a star. What it does is it burns hydrogen in its core. And it will keep turning redder and redder in this process as it goes older. Eventually, our sun will become something called a planetary nebula, something like the figure on the left. And if it's a more massive star than our sun, it's going to explode, gigantic explode, and become a supernova. So in those final stages of a star, gas is going to be ejected. And at first, the ejected gas is going to be really diffuse and volume filling, something like the Orion Nebula that you see over there. Over time, this diffuse gas is going to condense under gravity. It becomes denser and denser, like the Eagle Nebula over there, and eventually it becomes so dense that it can actually collapse on itself and create new stars. And that forms an active life cycle. In fact, in our Milky Way, on average, about 1 to 2 stars are created every year. So our galaxy, a recap, we live in this spirally, disky shape of a galaxy where the stars and gas are in this active life cycle in the galactic disk over there. So is our galaxy typical? You might wonder that. This image is taken by the Hubble Space Telescope that's staring at one small patch of the sky for 10 to 12 years. So in this image alone, it's very deep, meaning that it probes very deep into the universe. In this image alone, there are more than 5,500 galaxies. If we zoom in a little bit so you can see them better, you can see different kinds of galaxies over there. So do they all look like our Milky Way or not? Your answer is probably close to mine. Some do, some do not. So this is Hubble's galaxy classification scheme. So classify galaxies into different types just based on how they look. This classification scheme is sometimes called the Hubble tuning fork because of the shape. And the two big categories are one on the left, the E-type galaxies, E for ellipticals, and two on the right, S for spirals. The SBs are, B stands for bars, or spirals with a bar. So our Milky Way is somewhere around there. It's an SBC galaxy, spiral with a bar. Now, if the Hubble Ultra Deep Field image was fun to you, I highly recommend this website. You can Google the Galaxy Zoo project or Zooniverse. This website is indeed the Galaxy Zoo project. It is an amateur astronomy project where you can classify galaxies yourselves. So over the years, there have been hundreds of thousands of volunteers who have classified hundreds of thousands of galaxies. So as an example, I clicked classify on this website, and this is the image it gave me. This is an image from the James Webb Space Telescope. It's a really cutting edge space telescope of a tiny galaxy that's so far away, it seems really pixelated. It's too small. And you can select, based on your view, whether it's smooth or disky or something like an artifact. To my eye, this looks like a spiral, but it's actually a little hard to say because it's so far away. So if it's fun for you, go try it out yourself. All right, back to the tuning fork. If we squint and say, let's not care about the little subclasses, the SB, SBA, those are just telling you how tightly wound the spiral arms are. Then there are really just two big types of galaxies out there. One, the ellipticals, which seems red-orange-ish, and one, the bluish spirals, just like our own Milky Way. So you might wonder, what separates those two? These two are two poster childs of the two types. One is the blue spirally, like our Milky Way, and the other is red and elliptical. This is exactly the question astronomers try to answer. So we look into the physical properties of these galaxies and try to say what tell them apart. What we found was that the blue and spirally shaped galaxies have gas and are actively forming stars today, whereas the red and elliptical ones have stopped star formation as they no longer have any gas. Now, if we go back to this life cycle of gas and stars, and suddenly, somehow, you remove the gas from this equation, there's no gas left. What will happen is that the stars are already there. They'll still evolve and turn redder and redder. They will evolve to their end stages. They will eject gas, but the gas is somehow removed. So new stars will not be created anymore. In this talk, we will talk about how to starve a galaxy. And to starve a galaxy is to somehow remove the gas from it. Before we come to the investigation part, we will collect the puzzle pieces so far. So we have learned that our galaxy, the Milky Way, looks like a huge spiral disk. It contains stars and gas, which is in this active life cycle. But in the Galaxy Zoo, in addition to the Milky Way-like galaxies, there's also the other type, the red and elliptical-shaped galaxies. And what separates those two is the gas or the fuel for star formation. One has it and one does not. Okay, to start the investigation, you might want to ask, where do I find all those elliptical non-star forming galaxies? And this is the answer. So this is data taken from the Sloan Digital Sky Survey. And each line represents hundreds of thousands of galaxies into different bins. The different colored lines tells you how dense the galaxy environment is. And the y-axis tells you how many stars it is forming every year. what's drastic to me is how different the red line is with everything else, like the blue and the green lines. There are 10 times fewer stars being formed in galaxies at denser environments than the ones in more isolated, less dense environments. And there's an interesting line that stands out to my eye, which is the orange line. There seems to be some galaxies undergoing this active transition, going from the star forming, the blue and the green, to red, to non-star forming. Something's going on there. Then what are the densest environment for galaxies? This is not a creative name at all. They're called galaxy clusters because they're clustering together. Galaxies clustering together are flying by each other at a very high speed. This image on the left was taken by Columbia alumni Ari Chung and Columbia professor Jacqueline Van Gorkum. This is the Virgo cluster and all the galaxies that's flying in it. In the center of the cluster is not a vacuum space. So the plot on the right is showing you the hot gas, which is emitting an X-ray, super hot, that's filling the center of the cluster, and it goes denser and denser as you go near to the cluster center. This is taken by the ROSAT survey. Now, what happens to a galaxy in a dense environment? It's actually pretty close as what you experience when you bike around New York City. So if you bike really fast, you will experience this headwind that opposites your direction of motion. So the direction of this biker is to the left here, and the direction of the headwind is to the right. So a galaxy moving really fast in the cluster is going to experience exactly that headwind that goes opposite to this direction of motion. Bear with me for another analogy. This is very much like blowing a wind on a dandelion. Astronomers call this effect galaxy experience and headwind, something called ram pressure stripping. I will use this term interchangeably with the headwind because that's physically the same thing. But the stripping aspect is if you have a dandelion, which is something really fluffy, you can actually remove stuff from the dandelion when you experience a wind. Unlike the biker, who is very robust. So I'm going to think more about what causes or how strong this wind really is. The wind strength is dictated by two terms. One term is how dense your environment is. As you go closer to the cluster center, the environment becomes denser. And the other term is the velocity of this galaxy. So here, the first term, density gets higher when you're closer to a cluster. And the second term, I'm going to set the galaxy in motion. I'm going to ask you to stare at the galaxy and tell me when is this galaxy moving fastest versus slowest. Is this moving faster closer to the galaxy center or further away from the galaxy center? It repeats itself. Closer to the galaxy center is indeed faster, so the velocity will be higher. So if I pick 3 time frames from that orbit, this is T1, this is the second time T2, and that's the final time T3. Let's think about how strong the wind will be at those 3 different times. T1 and T3 are both very far away from the cluster center where the density is lower and the velocity is lower. While T2, density and velocity both higher. So indeed, the wind strength goes something like that. It goes up and down again. And if we're really lucky, we capture a galaxy at T2, something dramatic is going to happen. This is a galaxy where astronomers capture roughly at T2, where stripping or the wind strength is highest. The gas, so you're seeing the galaxy disk over here. The stellar disk is in the lower right, left corner. And the gas is stretched out into this gigantic tail in the other direction. So we know that the motion, direction of motion in the cluster is going here. And the direction of the headwind is, again, opposite the direction of motion is going there, which forms this beautiful gas tail. And the panel on the right is showing you a zoom-in view of the stars. You can kind of see the tiny tentacles following the stellar disk, and hence the name jellyfish galaxies, because they look like jellyfish. Now, in my PhD thesis work, I study galaxies under ram pressure stripping And because we don't have labs where we create new galaxies, we do that in the computer simulation way. So in my simulations, I have two main components of a galaxy. I have the gas components, the two panels on the left, and the star component, panel on the right. What I do is I set those galaxies in a wind tunnel. So I blow a wind on it that's simulated ram pressure. The wind will be showing something like this. We'll go in from one direction and we'll interact with the gas in the galaxy. So I'm going to walk through a couple of findings that we have. The first finding that stands out to us is that the diffuse gas around the galaxy is really easily lost. The 4 different panels from left to right shows you a time series where the wind goes stronger and then goes down again. So at t equals 0, there's no wind. T1, wind starts to happen. T2, wind is strongest, and T3, wind dies down again. The 3 different rows shows the total gas, so dense and diffuse, the dense gas, and the diffuse gas component of that galaxy. Remember that dense gas is what's currently forming stars, and diffuse gas is the reservoir or the gas tank that has a future potential of becoming dense and form new stars. Remarkably, the diffuse gas, like a dandelion, is blown right away when the wind hits. Now, if we zoom in to the dense gas part, what happens when the wind interacts directly with the dense star-forming gas? I'm going to play a video of how that process plays out. So now the wind's starting to hit the galaxy. Now is roughly when the wind is strongest. And the ram pressure stripping is active. And now the wind dies down a little bit. And the galaxy becomes smaller. So indeed, some of that dense star-forming gas is directly removed from the galaxy disk. And now the process goes again. Okay, so dense gas can be directly removed too. But imagine under the same wind, you have a smaller galaxy at play. So this is a tiny galaxy where the same wind is going to blow on it. What's going to happen? Same stripping. Gas gets directly removed. And very few gas is left in there. The gas is almost gone. Great. All right, so I'm going to take a pause here and talk about something slightly different. This is a really good question I got asked a lot. That is, are the simulations real? On this plot, I have a lot of beautiful real galaxies. The Magellanic Stream, for example, is what my advisor did in her PhD thesis, what Mary did. And the jellyfish galaxies on the right. And there's a tiny jellyfish that's about to become jellyfish on there. But we have an imposter. So the simulation is really not modeling a real galaxy one-on-one. It is not trying to recreate a real galaxy. However, it is still really useful because instead of a snapshot that we observe, we can see the time evolution of how things come to be. So these are the 2 things astronomers do. One is we understand what's out there in the universe, and 2 is we try to understand how things come to be. And simulations, by solving those equations, we can understand how this wind and galaxy gas interact. Okay, so now we move to the final part of this talk. Let's first summarize. Directly removing the gas will starve a galaxy. So if you have this strong wind that directly kick out the star-forming gas, then you will become from a blue-shaped spiral galaxy to a red galaxy. But that is not the only way. So this is a cartoon showing you the process that we just walked through. The pink is the so-called gas reservoir, which is the diffuse things that can rain down to the real galaxy and become the star-forming gas. And the blue gas is the active fuel for star formation. The second panel is when the wind hits, gas gets removed. And indeed, the galaxy will become red very soon. However, there's another way. Imagine you go on a road trip with a full tank of gas, and then you drive and drive and drive and never stop at the gas station. So you don't have any replenishment, and you just consume a lot of gas. So in this way, you're going to end with the exact same outcome, which is you end up with no gas and a redder galaxy. But this process is a lot slower than the first one. So the first one, 0.2 gigayear is a typical timescale. It's super long compared to our life stage, but is pretty short compared to the gas consumption. It's like 5 times, 50 times slower. There are also other ways like collision, but we'll not talk about that here. Okay, so finally, what will happen to our galaxy? We've talked a lot about gas stripping and starving. Is that going to happen to our galaxy? This is showing you our local galactic group, so Milky Way and Andromeda, in the larger galactic neighborhood. You can see the big clusters where the white dotted galaxies are really dense, and our galaxy is really not in one of those regions. So not in the dense environment, probably not going to be directly stripped. However, as many of you have correctly answered in the trivia, we are on an active collision course with our sister galaxy, the Andromeda Galaxy. So astronomers measure the proper motions or the current velocities of our Milky Way and M31, and we found that, whoops, they're actually heading toward each other. And the collision is predicted to be happening in 4.5 billion years. So depending on how optimistic you are, we're probably fine for another 4 billion years. I wanted to give a shout out to our Columbia alumnus book, Moya McTeer. She wrote this book called The Milky Way that talks about this very process in a really, really fun way. So if you're interested, definitely give it a look. All right, so today you've learned a really, really useful skill, that is how to starve a galaxy. And that is to directly remove the gas from it. And this is the time for questions. I thank you so much for your attention. Thank you.
Great. If you like that.
Sorry.
Can you advance one more slide?
Yes.
Okay, so Jingyao is going to take questions. If you want to not ask your question out loud, but submit it anonymously, you can scan this QR code or go to the link and type your question there. I will call on folks, and every question I'll repeat out loud before Jingyao answers. So, question? Okay, let's do one and then we'll come back.
The gas is being diffused, so to speak, and then losing all that gas.
Mm-hmm.
Do the planets at the periphery sort of go out of the orbit too? They orbit themselves.
Yeah, so as galaxies lose their gas, does that affect the planets and especially their orbits in any way?
Great, yeah, that is an awesome question. So we talked about the two components, the gas and the stars component. Stars and planets are kind of similar, as in they're this really tiny bodies, tiny high density bodies compared to the gas, which is really fluffy and diffuse. So ram pressure stripping will act strongly first on the gas and then on the stars, because it is a hydrodynamical process, so acts primarily on the fluids. And the stars are, compared to the gas, are like point masses, and planets are even smaller. So indeed, some stars might get kicked out, but that's very rare compared to the gas. If we look at one of those movies, I'm not showing the stars because they're not that affected, but very few of them would occasionally get kicked out. So not as affected as the gas.
That exists on the...
So there exists orbiting planets? Oh, orphan planets. Yeah, so planets that have been kicked out from their stars.
I would not be the person to answer that question, but there are many exoplanet experts in this department who will answer that. But yes, planets can get ejected.
Yep. Question?
When you refer to wind that's flowing, are you talking about the galaxy as it progresses through the interstellar medium? Or is there some other function that you're trying to describe?
So question about this gas or the wind from the galaxy, is that caused as it goes through what's called the interstellar medium or something else?
Yeah, that's an excellent question. So this wind is an analogy for the relative motion indeed as the galaxy moves in the medium. And this medium here is not the interstellar medium, which is often referred to the gas that's in between stars. It's something called the intra-cluster medium. So the hot diffuse gas in those big clusters, that's where the galaxies move in. So indeed, that's the headwind caused by moving in the intra-cluster medium.
Gas that's, yeah.
Yes, yes, exactly, yes. Yep.
Did you have a question?
Yeah. And other non-astronomy.
That's great.
So what causes the wild movement of all these galaxies through space? Like is there like a gravitational giant thing somewhere? Or, yeah.
Yeah, so excellent question. What causes these galaxies to move through the medium that then causes the wind?
I was enthusiastically nodding because you're very correct. It's because of gravity. And why is there this big gravitational ball that is in the center? It's because of how structure forms. So there's something called cosmology. Structures will collapse onto nodes and form those dense nodes occasionally. And galaxy cluster is one of the densest nodes out there. So galaxies orbiting a cluster is really just dictated by the gravitational pull that it feels in the cluster.
Well, what's that? Thing.
This gravitational thing is not shown in the existing slide, but is in one of my extra slides.
The thing I love about astronomy is all of these questions are questions that someone has researched. They've either looked at the universe or they've made computer simulations. So all of these questions are totally fantastic questions.
Absolutely. So this is not directly related to galaxy cluster, but the physics is exactly there. So those two curves are something called the rotation curves of the gas and stars in M33 galaxies. What we observe is the one with extra dots, the yellow and blue dots up there. And what we expect from existing mass, stars and gas in the galaxy, is the dashed line that's low there. There's a big discrepancy between the observed and the expected. And that is asking for more mass to pull the galaxy or the stars and gas together. And this extra force that pulls things together is something called dark matter. So dark matter is the missing mass that contributes to this gravitational pull that holds everything together. So in your galaxy cluster scenario, it's also dark matter that holds the galaxy to moving very fast together. And in fact, dark matter is way massive than normal matter. So normal matter is like 5% of the total mass, and dark matter is 25%. So that's 5 times more massive. And it's dark because it does not interact with photons. It cannot be detected in any way, except for this way, the gravitational way.
I'm going to do one online. So Jinyao, you talked about this like recycling process of gas and stars. Is every new star formed by gas, that recycled gas, is it smaller than the original star?
Ooh. Yeah, I would say the answer is probably no. So the recycled gas can be really massive. So if the thinking is that you have less mass than what you originally had, therefore all the stars are smaller, this is really not a one-on-one thing. So there are many, many stars contribute to the gas that's ejected. So it's really a collective effort of many stars ejecting many gas. And that many gas will collapse to form likely bigger stars. So it's not a lossy recycling process.
Question?
Mentioned what the wind and draft I was wondering what the speeds at which these galaxies are moving, and how much of these simulations that we do is more Newtonian than some relativistic effects.
All right,
Great.
so question first, how fast are these galaxies moving? Are they moving as fast or even faster than the Milky Way and Andromeda coming together?
So yes, I don't know the number in miles per hour, but it is very comparable to the Milky Way Andromeda relative speed. So it's probably 2/3 the movie that you show the orbit, probably 2/3 the velocity, relative velocity of Milky Way and Andromeda. So these are the typical velocities that galaxies move.
And that was 600,000 miles per hour.
4,000 miles, 400,000 miles.
Yeah, so maybe 400,000 miles per hour. And then your second question was about the simulation. So do you have just Newtonian gravity, or do you have things like that Einstein came up with, special or general relativity?
Yeah, for my simulations, I only include Newtonian because it will be cheaper. They're still really expensive. It will be cheaper to do because the Einstein modified gravity would apply to much, much denser environments, like around the black hole. But our scale here, our physical scale here, is much larger than a black hole scale. It's a huge galaxy scale. So Newtonian gravity does a pretty good job here. So we do that.
Question?
Okay, so what's the map when the galaxies go on?
So if I could interrupt, because I love this.
Mhm.
So I'm going to ask your opinions. So we know these galaxies are going to collide in a couple billion years. The Earth may or may not be there, depending on if our sun destroys it, but we're going to ignore that fact. So if the Earth was still here, raise your hand if you think, oh no, that doesn't bode well for the Earth. And the other option will be, maybe we'll be fine. So the pessimists, oh no, that doesn't seem good for the Earth, raise your hands. Okay, and the optimists probably will be fine. Raise your hand. Okay, and I'll let Jing Yao reveal the answer.
When two spiral galaxies collide, a really messy thing is going to happen. All the stars are going to form this gigantic, weird shape. And there will be sometimes a starburst. So all the gas becomes really dense, and it will create a huge bunch of stars. And the environment is going to be really hostile for the Earth, in my mind. And many of the big red ellipticals are actually formed this way. So the spiral arm structure are lost in that huge collision structure, huge collisional process. And all the gas merged together is going to be consumed super fast in the collision. And eventually you're left with a big elliptical.
Follow-up question. Is it similar to
Follow-up is it similar to a nuclear explosion?
I would say it's slightly more powerful than that, just because the huge scale.
But also, we say galaxy collisions, but really the stars and the planets, they're not colliding at all. When we look at pictures of galaxies, and we told you there are hundreds of billions of stars in the galaxy, so you think they're very dense, but they're really big. What we're seeing is pictures of galaxies that are so zoomed out, but galaxies, like atoms, are mostly empty space. So the gas will be disrupted, but the stars and the planets most likely won't touch each other. This is an analogy that I like, is if you have two cathedral-sized bubbles. So we have St. John the Divine on 1/12 in Amsterdam. Cathedrals are super, super big. If you have a fly, like a house fly in each of them, and then you throw the bubbles at each other, the likelihood of those two flies colliding is the same as two stars colliding. So very, very small chance. Question? Yeah, so how does the lifetime of our sun compare to when the collision of Milky Way and Andromeda?
I'm gonna divert that question to Amanda, because when the sun goes red giant, I think it's a couple billion years, but so comparable, but I don't remember the exact answer.
Yeah, so I'm also not an expert, so any grad or undergrad in the room who wants to correct me, please, please, please feel free to do so. We're not actually sure exactly how long our sun has. We know it's billions of years, so remember, we love to estimate roughly. So that's good enough for astronomers, but as Jing Yao said in her talk, as the sun begins to die, it's going to become redder, and the outer layers of the sun will begin to drift. So the sun will get poofier and poofier. And some estimations say that those layers will go all the way past Mars, which is definitely past the Earth. So even though those layers are a little bit cooler, the Earth will definitely be burnt up. Some estimations say it won't go that far. Either way, as our sun starts to die, or the climate on Earth will really change. So it will not be good for life on Earth, but we're not exactly sure. It's probably before the collision, definitely before the collision will end and the two galaxies will be their new Milkomeda. Forms, but we're not totally sure. Okay, I'm going to do a question online. How do you think when our galaxy collides, will the Earth exist, or at this time will Earth not already exist due to other reasons? So maybe I answered that with our sun maybe destroying the Earth by that time. Okay,
Great.
Let me just make sure nobody knew. All right.
Since you mentioned, you compared the thickness of the galaxy.
Ooh, that's a good question. Which is emptier, an atom or a galaxy? I don't know off the top of my head. I know atoms are about, it's either 90 or 99% free space. And of course, with galaxies, it really depends on the type. Whereas atoms, I guess, are a little bit more regular, but I don't know off the top of my head. Does anybody else here? This is where I would say, look over there as I Google.
Yeah. I have a bad answer to that. So the stars might be really far apart, but the gas is everywhere.
Yes, Jingyao is the gas gal. So she would say galaxies are denser because of the gas. That's a great point. Question. Do elliptical galaxies rotate like spiral galaxies?
That's a great question. So I think stars in elliptical galaxies have a way smaller rotation velocity. They're so-called more dispersion supported. So their motion is more random in stochastic directions, as opposed to the disky ordered rotation. So compared to spirals, they're definitely less rotation supported and more dispersion supported, so random motion supported. But I think there's evidence for some kind of rotation still in some ellipticals. So.
Yep.
Yeah.
Yeah, so is there any chance these red gas-starved galaxies could get new gas and then start forming stars?
Great question. So gas exists in different shapes and forms. And sometimes when you're lucky, there'll be streams of gas that's attracted by the gravity of a galaxy. In that case, you get something called inflows. So not starvation, but replenishment. So sometimes gas do fall in to galaxies that's no longer forming a lot of stars, and that will rekindle the star formation in galaxies.
Okay, question.
Yeah, I'd like to know, have there been any attempts to map the flows of these winds that just are blowing on galaxies? To see like if there's like a
Yeah, has there been any attempt to map the winds on galaxies or maybe the inflows, outflows?
Absolutely. So the jellyfish galaxy that you saw, I think here, yeah. So this is actually kind of a map of gas flowing out of a galaxy, but the direction of motion is on the plane, so that's hard to measure. But if you have a jellyfish galaxy where the direction of motion is in or out of the plane, that's what we can measure. And many of those jellyfish are actually measured. So their velocity out of the galaxy is a couple 100 kilometers per second.
They can account for 3D space here.
Definitely, yes, yes, yeah.
I guess this is what is basically cutting edge. It's really in the process of really studying this.
Absolutely, yeah. People map those in different wavelengths. So H alpha, CO are different gas tracers. So people do.
We had another question here. Yeah.
Go back.
Oops. Yep.
Okay, so here, where would
So in these different galaxies, where would gravity be the strongest, or so across all the pictures?
Good. So rather than how they look or what's their morphological type, where would gravity be strongest would be a question of how massive the galaxy is, because gravity is directly proportional to the mass of the galaxy. Typically, the elliptical galaxies are more massive because they're often created in collision. So they're a collision or a collection of many, many smaller galaxies. So if, say, one of those ellipticals are really massive, then gravity is strongest there. But it's really not dependent on the type or the shape, but more on the mass.
Okay, I think we'll do one more question, then we'll do our raffle, and then I'm sure Jingyao will stick around for a little bit more if there are other questions. So our final official question.
So you go back a little bit on that equation for density
Uh-huh.
and the velocities.
Yes.
It's a really simple.
Yep.
Does that actually work if I was, does that equation actually work if I was writing it like?
So could you take this equation, wind strength equals density of the air times velocity that you're going? Could you do that as you ride a bike and figure out your own wind strength?
Equation.
It is the same equation. This is a definition pressure. So it's a definition of that wind that you feel, but the air density doesn't change too much. So it's really just the velocity, how fast you're going.
And maybe it's easiest to measure velocity and the wind speed and your speed, and then you could calculate the density of the air that you're going through.
It's velocity relative to the air or relative to?
It's the relative velocity between the air and you. So if there's a wind, you have to add that in. Yep.
Okay, so we have 3 astronomy mugs to give away today. The way this is going to work is there is a number on the back of your chair. So if you turn around and look at that number, I'm sure these numbers are for some scary physics testing reason, but today we're going to be giving stuff away. So if I call your number, or if it's the seat to your left and it's empty, if you're on the end, it can be the one to your right and it's empty, you can claim that seat. Okay, our first one is L9. Is anyone in L9? All right.
Woo!
Feel free to come down and get a mug or get it as you leave. You do not need to do these stairs. I'm not going to do them, so. Okay, of course, thank you. Okay, and this is where we'll see. Let's see, do we have anyone in E2? No? Okay, K8. Okay. What about A12? Oh, all right. Thank you. Okay, D11. Oh, so close. That's like us checking the weather. H13, G18, K2, I3. We're not striking out here. B11. B11, all right. Of course. Okay. Thank you all so much for coming. We're very sorry that we can't observe. We wish we could control the weather. A lot of my friends in graduate school would say they wish we could get rid of the atmosphere and then we would have no weather to deal with. But we'll have other events throughout the summer, so fingers crossed observing will happen then. And if you have any other questions on your way out, we have a bunch of grad students who don't have to work. It's Friday, but if they wanted to help answer questions, they could. Thank you all for coming out.